Hello, in this video, we'll continue to talk about passive components, specifically capacitors. We'll also be talking about different types of capacitors, how they work, how they differ from batteries, and an RC circuit. Now, exactly what is a capacitor? Well, it's a passive component that stores electrical energy by gathering electrical charge between two closely spaced plates, and those plates are isolated from each other. This shares a common ancestry with the battery, as both were developed from the Leyden jars of the mid 18th century, but the two are not the same. Early capacitance was an aspect of these latent jars, but it really wasn't until Michael Faraday in the 1830s that capacitance really had a name. But by the 1870s, there were simple paper and mica capacitors that were used in telegraphy. Although it wasn't really until the 1920s to 1930s that you saw specific capacitor components being sold. They're measured in farads, which is designated by a capital F, and again, they're named after Michael Faraday. Hobbyists will usually be dealing with them in microfarads, nanofarads, and millifarads. They come in a variety of different values and materials. Electrolytic and ceramic capacitors are the most common, and electrolytics are also further divided into aluminum and tantalum. If you don't see material mentioned for an electrolytic, probably just assume that it's aluminum. Capacitors can be either polarized or non-polarized. We tend to see them polarized for electrolytics and non-polarized for ceramics. And generally speaking, the polarized ones will work in a pinch in place of non-polarized, but always check your data sheets. So wait, isn't a capacitor just a battery? Well, in the sense that they both store electricity, yes, but actually a battery and a capacitor are two totally different things. A battery converts chemical energy into electricity, while a capacitor simply stores an electrical charge. Capacitor's purpose isn't to act like a battery either. The charge is meant to be stored and discharged very quickly, so they are more for a smooth flow of power when there are tiny little fluctuations that last very brief periods of time, such as nanoseconds. All right, here's a picture of an aluminum electrolytic capacitor. If you find those on somewhere like Amazon or DigiKey, they'll probably just be called electrolytic capacitors. Um, but this is a pretty typical appearance for them. They just vary in size due to value. It's actually not facing in a way that you can see either the polarity or the value. Although you can see that it's produced by Nichicon, which is an electronics company that makes a lot of components, and they're basically a household name in electronics. Here we have a picture that has a selection of tantalum electrolytic capacitors. These are a little less common to encounter, although you will find them in plenty of electronics, and it can be just a bit more expensive than aluminum, but they have a few advantages over them as well, although they also have their disadvantages, such as they're able to be shorted. Lastly, we have ceramic capacitors. These are usually non-polarized and of relatively small value, such as the nanofarad range. They're really good for filtering out noise in that range as well. Now, Kirchhoff's laws of voltage division and current division still apply to capacitors, much like they did with resistors. However, there's a little bit of a difference in behavior here. A resistor merely resists the flow of electricity. It reduces current and voltage, and it dissipates that as heat. But capacitors store the flow into an electrical charge. This means that capacitors will only draw current until they're full or close to full, and this is a relatively instantaneous, so it's difficult, if not near impossible, to actually see the different current draws between parallel capacitors of different values. You might be able to add a switch to control the points of charging and discharging, but aside from ideal circuit simulators where you can heavily reduce the time simulation, you might not actually be able to see it. Now, as I mentioned, capacitors in series will divide voltage at each node so that two capacitors can be used to get 3.3 volts from 5 volts, for example. This doesn't actually affect their storage capacity any more than it would affect the resistor values. If they're in parallel, they will divide the current, although because of the constant charging, discharging, and it all being fairly instantaneous, you might not be able to observe this. Here we have an example of capacitors in series using Felsted. We have three 10 microfarad capacitors, so they're dividing the voltage into 3.33 and 1.66 volts respectively. With a lot of working, I finally came up with a circuit that sort of shows the difference in currents, so that each capacitor is being charged by a different level of current. Um, and even then, the scale feels wrong. But yeah, this is sort of 100 millifarad, 200 millifarad, 300 millifarad farad. And as you can see, it's at different rates. All right, let's move on to what's known as an RC circuit. It's basically a basic circuit that's made up from a power source, resistor, capacitor, and ground. The use of the resistor changes the charge and discharge times of the capacitor, so it's no longer instantaneous or near instantaneously. You can calculate the time it takes for the capacitor to charge up to 63.2% of its capacity. Likewise, you can calculate the time it takes for it to discharge down to about 36.8% of its capacity. These numbers aren't random. They have to do with exponential decay and growth and concepts of the mathematics of exponential behavior in circuits. This time is known as the time constant, and we use it to measure how fast the circuit actually responds. And it's indicated by the Greek symbol tau. We've already mentioned what happens after one time constant, but at two time constants it charges up to 86.5, and at 3 it's up to 95, and then finally at 5 it's at 99 or basically fully charged. When discharging after time constants, it should have reached nearly zero or basically discharged. So 5 time constants to bring it completely fully charged and 5 to completely discharge it. All right, we have every circuit loaded up, and I have an RC circuit right here. It's not doing much of anything yet. But and I have a switch set. Um, the top is going to charge the circuit, the bottom is going to discharge it. And obviously, it's through a 1K resistor, which is going to mean that it's not going to instantly charge or discharge. Now, we've done the math with 1 volt, a 1000K resistor, and a 1 microfarad capacitor. We should have a charge and discharge of about 1 millisecond. So let's run it and see what we see. Okay, let's charge it. Let's discharge it. Let's pause it and let's look at it. The curve right up here at the top is the same as on the bottom because again, we're only using one resistor. There is ways to change this so that the charging and the discharging are different times using a diode, I believe. All right, so let's move our numbers around. So we're looking at 63.2, as this is a 1 volt power source. Let's see, or 62.3, I believe. Let's get it kind of close. All right. See where it stopped. And yep, now this is a tiny bit off, but yeah, 63.8 and yeah, 1 millisecond. Well, let's look at the other side. That's going to be, I believe, 38.2 once it discharges, same numbers. So and yeah, it's just about 1 millisecond there, give or take. So again, this is what an RC circuit does, and it actually can be pretty powerful in a number of applications. All right, let's just wrap things up here with a bit of a recap. Capacitors store electrical charge, usually very small amounts for small, brief periods of time, unlike a battery. The two are definitely not the same. One stores charge and the other converts chemical energy to electricity. Capacitors are usually measured in farads, and our capacitors will probably be microfarads, nanofarads, and millifarads. They come in a number of different packages and materials, but we'll mostly be using aluminum electrolytics and ceramics. Capacitors in series and parallel, they still operate under Kirchhoff's laws, but they work a little bit differently in terms of behavior compared to resistors. We did make an RC circuit, which allows you to control the charge and discharge times of a capacitor, and that time is known as a time constant, which is designated with tau. Well, until next time, have a good one.